Transmission lines, line transients, part 2, series on transmission line theory, lecture number 2.41. This is second session on line transients. In this session, we focus on pulse forming lines and also on reflection diagrams, voltage reflection diagrams and current reflection diagrams. Lines are used mainly for the purpose of carrying signals from one point to another point. Transfer of signal from one point to another point is considered as the primary application of transmission lines. In addition to the primary application, there exists several secondary or auxiliary applications for transmission lines. Examples are pieces of lines are used to fabricate inductance, capacitance, and also resonant circuits at high frequencies. One such another secondary application of lines is in generating ultra short pulses. Pieces of lines with the open circuit at one end, they are used to generate pulses which are very short, ultra short. In addition to these lines which are called pulse forming lines, in this session we also study about reflection diagrams. What are reflection diagrams? When a lossless line has mismatched conditions on both ends, then there exists huge number of waves over the line as a result of multiple reflections from the line ends. Sometimes it is required to know the voltage, the current at an arbitrary point over the line at a particular instant. In such cases, reflection diagrams are highly useful to give the required information. Now let us move further to the session proper to study and to understand pulse forming lines and reflection diagrams in a comprehensive manner. We begin with pulse forming lines. An important application of lossless line pieces is in the generation of ultra short pulses. To understand how line pieces are able to produce ultra short pulses, consider an open circuited transmission line charged to V0. Let us suppose its characteristic impedance is Z0. As the line is lossless one, Z0 becomes pure real. This line is connected to a resistor Rg at source end. Load end is open circuit. After the switch closure, current starts flowing through the resistor as shown in the figure. A current wave with a positive step wave front I1 plus and simultaneously a voltage wave with a negative step wave front V1 plus start traveling towards the load end. Notice current is a positive step whereas voltage is a negative step. Their amplitudes are V1 plus is equal to minus V0. V0 is the voltage to which the line is charged initially. Z0 is characteristic impedance of the line. Rg is the resistance that is connected across the line at the source end. Z0 is Ci, characteristic impedance of the line, as already mentioned. So amplitude of the voltage step V1 plus is given by this formula. Whereas amplitude of current step is I1 plus is equal to V1 plus by Z0. The line is illustrated here, lossless line with OC. On one side it is open circuit, characteristic impedance is R0. Source side it is connected to certain resistance Rg. The line is charged to certain voltage V0. This is the situation before line is switched to resistor Rg. After switching, what happens? Current wave step starts moving towards output side. A voltage wave also, of course, voltage wave amplitude is negative, current wave amplitude is positive. Now the total voltage over the line is the voltage that is charged to the line plus the wave. Now, a detailed description of the functioning. A charged line can be found equivalent to uncharged line with a source V0 connected between Rg plus terminal and top conductor minus terminal. Now the charged line is an uncharged line sourced by V0 with an internal resistance of Rg. If Rg is equal to R0, then V1 plus becomes minus V0 by 2. This voltage step then takes a time equal to L by C. L is length of the line, C is velocity. Velocity cannot be C because C is velocity in free space. But as the line is lossless, velocity is near to C. So here C is used. A time equal to L by C to reach the open end, and during travel it reduces the voltage over the entire line to V0 by 2. The voltage across the resistor now becomes VR equal to V0 plus V1 plus, which is equal to V0 by 2. At the open end, the voltage wave gets reflected completely because it is open circuit. At open circuit, at short circuit, or when termination is pure reactance, reflection is total. So here the load is open circuit, so reflection is complete. Therefore, V1 minus is equal to V1 plus equal to minus V0 by 2 and travels to source end, reducing the line voltage as well as voltage across the resistor to 0. So a voltage persists for a time of T capital T equal to 2L by V in the form of a pulse across the resistor. Such a line with Rg equal to Z0 when used for pulse generation. These lines are called pulse forming lines. Pulse formation can be considered as one of the secondary or auxiliary applications of lines. Lines are used for load matching purposes. Lines are used for measuring impedance. Lines are used to fabricate inductors and capacitors. These are all secondary applications. Pulse formation is a secondary application of lines. Here is shown pulse formation, voltage pulse. Then in B is shown current pulse. Amplitude of voltage pulse is V0 by 2. Amplitude of current pulse is V0 by 2 or not. Duration of the pulse is 2L by V. L is length, V is velocity of the wave over the line. Now we move to another aspect pertaining to line transients. Voltage reflection diagrams and current reflection diagrams are simply reflection diagram. What are reflection diagrams? A simple method by which one can keep track of voltage at a point over the line is by means of voltage reflection diagram. It is a two-dimensional plot with the position on the line over horizontal axis and time on vertical axis. When the switch located at battery end, that is at x equal to 0, is closed at t equal to 0, a voltage wave starts and it corresponds to origin in the diagram. The location of the leading edge of this wave as function of time is indicated as diagonal line that joins the origin to the point along the right hand vertical line, which corresponds to time t equal to L by V. L is length of the line, V is wave velocity. From there, the position of leading edge of reflected wave is shown as another diagonal line joining the point at t equal to 2L by V on the ordinate. From there, the wave reflects again, another diagonal line comes into being and it continues forever. The voltage at a given point over the line is a function of time and it can now be found by drawing a vertical line at the corresponding position to this point over the diagram. This line then intersects various diagonals representing different forward and reverse waves. By adding the voltages of all these waves, the voltage at the desired location of line can be obtained. The addition has to be performed beginning from the bottom of the diagram and moving upwards. Whenever a voltage wave crosses the vertical line, its value has to be added to the total voltage at that time. An example can be considered. The voltage at a location 1/4 the distance from the battery to the load is plotted in the figure, which is going to be shown in the next slide. To obtain this plot, a line at x equal to L by 4 is drawn on the diagram, and whenever wave crosses this line, the voltage in the wave is added to the voltage that has accumulated at x equal to L by 4 over all the earlier times. This is voltage reflection diagram or diagrams. Here two diagrams are shown, one in A, one in B. Everything starts at the origin. When source is switched on, a wave starts traveling towards the load end. It takes a time equal to L by V to reach the load end. As the load is mismatched, if it is matched, then there won't be any reflected wave. Reflection diagrams, they are mainly meant for finding conditions over the line when the line is under multiple reflections. So at both ends, line is under mismatched conditions. So at load end, again a reflected wave comes into being and it starts traveling towards the source. It also takes a time equal to L by V to reach source from load. Therefore, at an instant equal to 2L by V, the reflected wave or first reflected wave reaches the source. Again, reflection happens. It takes another L by V time to reach load. So total time or the instant at which the second forward wave reaches the load is 3L by V. Like this, one can keep on drawing the waves. But notice when time is less than L by V, over the line there exists only one wave. In between, L by V and 2L by V, two waves are there. In between 2L by V and 3L by V, there are three waves. 1, 2, 3. Between 3L by V and 4L by V, four waves. So as you move away in time, more and more waves come into being over the line. It means voltage at a point over the line is contributed by all these waves which are existing over the line up to that point of time. When time is very large, all the waves then contribute to the voltage at a point over the line. In B is shown voltage variation at a point over the line. This point is at a distance of L by 4 from the source end. Before T less than L by 4V, there is no voltage. Wave started traveling. This is x equal to L by 4 point. Wave started traveling here. To reach x equal to L by 4 point, it takes some time. Before that instant, before that time, voltage is 0. So here it is 0. After L by 4V, because of first forward wave, certain voltage has come at this point. After 2L by 4V, at this point, now there are two waves, one forward, one reverse. Both contribute to the voltage. It is V1 plus V1 minus. So as time passes, more and more waves start contributing to the voltage at this particular point. Now, what is the importance of this diagram? From these diagrams, for example, from B, just by mere looking at the diagram, one can know the voltage at a point over the line at different instants of time. At t equal to more than L by 4V, less than 2L by 4V. What is the voltage? At x equal to L by 4, it is V1 plus. It doesn't require much calculation. We are saved from doing complicated computation. Similarly, if one is interested to know the voltage at x equal to L by 4, when the time is between 15 L by 4V and 17 L by 4V, one can find from this diagram. Suppose to sketch the diagram in B, first we have to do diagram given in A, which requires gamma L, gamma G. From A, one can derive, one can sketch diagram B. After voltage reflection diagrams, now we move to current reflection diagram. The line current can be found in a similar manner through current reflection diagram. The easiest way is from voltage diagram directly by determining the value of current that is associated with each voltage wave. While doing so, a standard convention regarding the polarity of current is associating positive current with forward wave and negative current with reverse wave. Once the current diagram is sketched, current at a given location and time can be found in the same manner as voltage is found from voltage diagram. Here is shown the current reflection diagrams. This is starting point. This is current wave amplitude. It reaches the load end after traveling a time of L by V. Reflection happens. Reflected wave then reaches the source end at 2L by V. Again reflection happens. Reflected wave travels, reaches load end at 3L by V. The procedure is almost same as followed while sketching voltage reflection diagrams. In B is shown current over the line at a point at different instants of time. Before t equal to less than L by 4V, current is 0. Then current has increased. After L by 4V and before 7L by 4V. As already mentioned, by following the procedure similar to that followed while sketching voltage reflection diagrams, current reflection diagrams can be obtained. Of course, to get B, first one has to sketch A. These are some of the points which I have, which I want to share with you for right now. To recap, in this session, the second session and the last session on line transients, we focused on pulse forming lines and also on the reflection diagrams, voltage reflection diagrams and current reflection diagrams. Hope you have a beautiful, enriching learning experience. See you soon again in another session. Bye bye.